All right, here we are again, another lab. This lab we're going to do is very similar to the last week's lab we did with Chatelier's principle, but this time we're going to do actual calculations, numerical values with our equilibria constant. Remember, Le Chatelier's principle was based on a dynamic equilibria, and the dynamic part of the equilibria is very, very important. Consider a real simple reaction that everybody always uses: A plus B goes to give me C plus D plus D. And if I looked at the rate of the forward reaction, my rate would be equal to some K. K is the constant, proportionality constant that's used in here, times the concentration of A raised to some value, times the concentration of B raised to some value. Those come from the rate limiting step, right? They're the balanced chemical equation for the rate limiting step, and they need not be associated with these values down here. Well, as this reaction goes forward, A gets smaller and B gets smaller. The concentrations go down. The concentrations of C and D increase. Well, there's also a reverse reaction. Say this is R forward, this is R reversed, and that's going to be equal to K. They usually give it K minus 1 to indicate that it's the reverse direction. And that's going to be times C raised to some power and D raised to some power. We can put Z and W over there, because again, these come from the rate limiting step from the balanced chemical equation. So as the reaction proceeds forward, concentration of A and B get less, the rate slows down, C and D get greater, the reverse rate speeds up. Eventually they meet somewhere where as the rate goes forward and creates it, the rate backwards decreases it, and we reach an equilibrium where we have equal values, equal rates in the directions is the way you can think of it. Our concentrations appear static, but it's a dynamic equilibria that's going on. That's why Le Chatelier's principle works, that if we disturb it, it will adjust to correct it. And this is usually given by KEQ. Now notice this is a capital K, not a lowercase k. Lowercase k for kinetics, capital K for equilibria. And that's going to be equal to this is your mantra, whenever you see capital K for KEQ, it's products over reactants raised to the coefficients from the balanced chemical equation. Not the coefficients that came from the kinetics, whole different thing. They're related, but they're different. This comes from the balanced chemical equation, which would be this. So that means we would have products over reactants, that's C raised to C times D raised to D over top of A raised to A times B raised to B. Okay? Remember the brackets here are species concentration, molarity. They're basically molarity. All right? So this is a constant, which means that these values, the product of the numerator over the product of the denominator here, the product of these two for our numerators, product of these two for our denominator, has to equal this KEQ value. Now, I guess you could have these down so small that it never got there, but basically it's always going to equal this KEQ value. Because this is KEQ, a K, it is a constant, so we can use that to our benefit to figure out things based on that. You'll probably use ICE tables, and that's probably what you were taught in the lecture. I hate ICE tables, primarily because they're just a trick that students can use to get the answer without understanding why that gives them the answer. And then I get those students in quantitative chemistry because I'm an analytical chemist, and I have to kind of unlearn them the bad things that they were learned in GChem 2. But, what can I do? I do what I can do. So I will show you ICE tables because that's traditionally the way a lot of gas phase equilibrias are done, not so much solution phase equilibria. But I don't like them, but I'll show you to them because I'm sure that's the way you were taught in lecture, and that's just the way we're going to do it. All right, so let's do an example, and we'll talk about some things that we need to consider. So example 1, for a system with dinitrogen trioxide reacts with hydrogen to produce nitrogen monoxide and water. Calculate the value of the equilibrium constant if there was 0.1908 moles of N2O3, 0.0908 moles of H2, 0.0092 moles of NO, and 0.0092 moles of H2O vapor present in a 2-liter reaction vessel when present at equilibrium. Where do we start? We start the same place we always start for almost all this stuff we do in general chemistry, and that is with a balanced chemical equation. We look at what they told us. They said that N2O3 put this in the gas phase, plus H2 in the gas phase is going to go to give us 2 NO. Remember, it has to be the balanced chemical equation, plus H2O in the gas phase. Now, when you're doing like liquid solutions and stuff, a lot of times water won't enter into your KEQ that you build up for this thing. This is gas phase. Water's just another vapor in the gas phase, just another molecule that's in the gas phase. So it has to be included in this case. All right. So let's look at that. The first thing we notice, let's build our KEQ. Our KEQ then is going to be equal to, well, what's our products? That's going to be NO squared, because there's a 2 here, times H2O concentration over top of N2O3 concentration times H2 concentration. Okay? Simple enough. Like I said, products over reactants raised to the coefficients from the balanced chemical equation. These are all 1, so these all raised to 1, so we don't have to show it. But the first thing we notice is, remember, these brackets are species concentration. Concentration in chemistry is molarity. So this is molarity. Molarity is what? Moles per liter. Not moles, moles per liter. So we are given so many moles of each gas, and we're given a 2-liter vessel, but that's not the molarity. The number of moles here needs to be divided by 2 liters to get it in moles per liter. So to be able to get the right values up here to do our calculation, we've got to convert everything into molarity. So let's do that. So what did we have? We had 0.1908 moles of N2O3, but that's in 2 liters. So the molarity we get is 0.0954 molar. Okay? And that's for our what? That's N2O3. So let's go ahead and put it in over here, 0.0954. Next is, let's say, the hydrogen. Hydrogen gas, we were given what? We had 0.0908, is that right? Moles of H2, and that's in 2 liters. So that gives us a molarity of 0.0454 molar. So let's put that in for our H2, 0.0454. Notice that you use brackets when you have the chemical species indicated for concentration. When you have the actual concentration values, you use the round brackets to indicate that, there's something different. It's just a way of differentiating it. I don't think you're going to have an exam on that, but if you understand what the symbolism is, it makes it a lot easier to understand what's going on. All right, so what's next? Next we have what? Well, we have our top, our NO, and we had 0.0092 moles of NO, but that's in 2 liters. So that gives us a molarity of 0.0046 molar, and that's going to be 0.0046 squared. Got to remember to square that. And then finally, the last one is our H2O, and we had 0.0092 moles H2O in 2 liters, and that's going to give us a molarity of 0.0046 molar. Sorry, didn't write that very well. 0.0046 molar. So now we've got all our values. All we got to do is just multiply them through and get our answer. We've got everything we need to figure out this KEQ. And we multiply that through, and we get 2.2 times 10 to the negative 5. Notice that equilibrium KEQs do never have units, because the units are so variable with every single one. So they just invariably they don't put units on it. So don't worry about sweating out the units. I mean, we could figure it out. This is moles squared times moles over moles and moles. So we take the 2 off of that, and this would have units of molarity. But we don't worry about messing with the units. Oh, I'm sorry, you couldn't even see what I was writing down there. 0.0046. Good, you didn't see that I wrote it so poorly. There's our equilibrium constant. All we got to do is figure out what these things are, plug them in, get our equilibrium constant. Easy peasy, simple as pie. So let's do one that's more, closer to what we're going to actually be doing in this lab. I'll use the back of the original handout, and let's do one here. So number 2. Initially, a mixture of, this has molarity, not moles, so it makes it a little bit easier. 100 molar of NO, and we had 0.050 molar of H2, and we had 0.100 molar of H2O. And that's allowed to reach equilibrium in a reaction that produces N2 in water, right? Isn't that what the reaction is? It says, no, at equilibrium, and then it says at equilibrium, the concentration of NO was found to be 0.062 molar. All right, so first thing we need to do is we need to come up with the balanced chemical equation so we can get our KEQ figured out, and this is going to be 2NO gas phase plus 2H2. The gas phase is going to go to give us N2 in the gas phase plus 2H2O in the gas phase. Lots of things going to be squared. So our KEQ is going to be N2 times H2O products squared over reactants, NO squared, and H2 squared. Okay, so that's pretty simple. Well, we know what the initial concentration of these values were. Obviously, our N2 is 0. N2 must be 0. And we know what equilibrium concentration of this one is, but we don't know what the equilibrium concentration of these others are. But it's just a simple algebra problem. So let's set it up. We'll do our ICE tables. ICE stands for initial. And the way I like to do this is we write down the actual reaction. We don't need the coefficients. The coefficients, you can put them in there, but they tend to confuse people. You need to use them in the calculations, but I'll put them in there. I just don't want you to get confused by them. So I have 2NO plus 2H2 goes to give me N2 plus 2H2O. All right, so I have initial. I have change, my delta for change. That's usually given as C for ice. And then finally, my equilibrium molarity. And then these are my individual pieces. So I know I started off with what? I started off with 0.100 molar here, 0.050 molar there. I had 0.00 molar here, and I had 0.100 molar here. Change, I'm not sure what happens, but I notice that it takes two of these, and the reaction is going in this direction, so it's going to be minus 2 of whatever the value of X is. Okay? This is also going, we're losing these. These are being subtracted out to produce these, so it's going to be minus 2X. This is going to be plus 1, so just plus 1X. It's not 2 X's. For every 2 of these, we get 1 of these, and this is going to be plus 2X. This is 2X because there's 2 waters over there. All right, so now we got to solve for X. See, that's why I don't like it, because X is different in every case, but we're solving for X. I mean, I could put this X and Y and Z, but that just gets even more confusing. So what do I know? Well, I look at the problem and I say, I know that this is 0.062 molar after the change. So it's an algebra problem, right? I've got what? Well, I had 0.100 molar minus 2x equals 0.062 molar. I just have to solve for x. So what do? Well, I take my 0.062 molar minus 0.100 molar, and that's going to be equal to negative 2x. So what is this value? This is negative 0.038 molar equals negative 2x. Therefore, I can divide through by a negative x, or a negative 2 on both sides, right? Negative 2 on this side, negative 2 on this side, and that's going to give me x on this side, and it's going to give me my value over here, which is 0.019 molar. So that's my x. Now I just take that x and I plug it in up here for everywhere that it was used. So this is going to be my 0.0500 molar minus 2 times my 0.019 molar. And that's going to give me a value of what? Well, My 2 times 0.019 molar, that's going to be 2, and then 2 nines is 18, so that's going to be 0.038, right? So this is going to be the equivalent of 0.038, and that's going to give me a value down here, 0.012. This is going to be plus 0.1, so that's 0.019. That's easy because it was 0. We just added 1 to it. This is 0.1 plus 2x, and we just said the 2x is 2, and then 2 times 9 is 18, so that's going to be 38. So it's 0.138 molar. So now we have all the values. To get our KEQ, we just plug it back in up here, and we say, okay, our N2 was 0.019. Our H2O was 0.138 squared. Our NO was 0.062 squared, and our H2 was 0.012 squared. We do a lot of squarings, hit the bunches of buttons on our calculators, and we get 6.5 times 10 to the 2. Notice that I wrote it that way. Why? Because if you write it as 650, that's 3 sig figs. Maybe the 0 here is ambiguous. Remember, we covered this in the first lecture or whatever. So we have to write it to indicate that it's 2 sig figs and have the correct magnitude. We have to write it in scientific notation. Okay? All right. So for the lab, you're going to be doing kind of like ice tables. What you're going to do is you're going to go to a simulation, and you're going to put in starting concentrations for a reaction that involves iron. It's, what is it, iron 3 plus SCN, and it goes to form FeSCN 3 plus. This is actually a reaction that we do in the lab when we're in the lab at UNF's campus. This is the reaction we do. And the simulation works great, and it's just as good. So you're going to end up with an initial concentration of these 3 things. I set it up, and I've already filled in the tables on the handout so that one of these are 0 each time. And you're going to hit the button and hold it down, and you'll see the change in the reaction in the different concentrations until they reach equilibrium. When they reach equilibrium, you're going to write down the values for equilibrium. You've got the initial concentrations that you put in. You should be able to come up with what the change is and fill out a table. And then you can calculate out the KEQ for each reaction. There's 3 different reactions because there's 3 different species, and you have a starting concentration that's different for each of the 3 species. And it's a nice experiment. And then there's some post-lab questions that you have to do. So don't put it off to the last second. There's a little bit to do there. The simulation doesn't take very long. Once you get it set up and get used to how it works, it'll take you, less than 5 minutes to do the 3 reactions that you need to do. Post-lab questions, you'll need to do a little bit of work, but it's not too bad. You should be able to get that done. And then get it in Tuesday at 9 o'clock. And next week, we'll do another lab. Till then, see ya. Try to be safe. Try to have fun. Don't know how you can do both, but try.